Hey guys, Mr. Long Break here. Today we're going to be talking about bond energy and how to use bond energy in order to solve for delta H. And if you remember, delta H is the amount of energy that is absorbed or released in a particular reaction or process. And two things happen in a reaction: bonds break and bonds form. And in order for bonds to break, energy has to be absorbed, meaning that it's an endothermic process. So you start off with reactants in a particular reaction. Those reactants have to take in or absorb energy in order for their bonds to break. Then when those substances form new bonds, energy is released. Meaning it's an exothermic process. So when your product bonds form, you release energy, and that would be an exothermic process. Now to find delta H, what we're going to do is we're going to take that amount of energy that is absorbed, subtract it by the amount of energy that is released to form those bonds, and you will find delta H in kilojoules per mole. Now an important thing to realize is what these two actually mean. And the amount of energy that is absorbed in a reaction means the activation energy. And that should sound familiar from last week's talk with potential energy diagrams, which is abbreviated E subscript A. And the amount of energy that's released in a particular chemical reaction is called the reverse activation energy. That should also sound familiar to you guys from last week, which is abbreviated reverse E/A. So that's another way of thinking about it and how it connects to potential energy diagrams, which I'll be showing you today. Okay, so now let's go through a few examples of how to actually solve delta H with bond energy. And in order to do that, you will always be given these bond energies. And those bond energies represent how much energy is needed to break each type of those particular bonds. And then these are the steps that we're going to follow down here. And if you look, there's 6 of them, and I'm going to tell you that these first 2 will always be done for you. We've learned about how to balance the equation. We've also learned about how to draw Lewis structures. For simplicity reasons, I'm just going to do that for you for each of the examples, but these are the 4 that you need to make sure you pay attention to and do with each example. Okay, so notice here that I separated the reactants from the products, and that's really important to make sure you do that distinction. And I'm going to start with counting the number of each bond and multiplying that number by the bond energy. And so what I want to do is on this reactant side, I want to look at all the different types of bonds. And if I look, there's one specific type of bond here that is a carbon bonded to a hydrogen. And so I'm going to write here carbon bonded to hydrogen, and the amount of energy required to break that bond is 413 kilojoules per mole. And I'm going to take that and multiply it by how many of those bonds there are in the molecule. Well, there is 1, 2, 3, 4, 5, 6, 7, 8. There's 8 carbon hydrogen bonds. And if I do 413 times 8, that is going to give me 3,304 kilojoules per mole. Now I'm going to do that same process for all the different types of bonds. Okay, so the next type of bond in that molecule is a carbon-carbon bond, which is different than the carbon-hydrogen. It's kind of hidden in the middle of that molecule. And the amount of energy needed to break that bond is 347 kilojoules per mole. And I'm going to multiply it by how many there are in the molecule. There's 1, 2 carbon-carbon bonds, and 347 times 2 is 694 kilojoules per mole. There is no other type of bond in that first molecule, and there's only one of them in the balanced equation. So I'm going to move on to the oxygen. And oxygen, or O2, is drawn next to it. And the main type of bond that's seen there is the O double bond O. And double bonds are different energies than single or triple bonds, so make sure you pay attention to that in the future. And an O double bond O In order to break that bond, you're going to need 498 kilojoules per mole, and I'm going to multiply it by how many there are in that particular molecule. Now, if you look, there's only one of those. However, there are 5 oxygen molecules in the balanced chemical equation, and this is important. So even though only one of them is drawn there, there are 5 of them that I need to account for. So I'm going to multiply that by 5, even though there's only one drawn there. And if you want to draw those, just to help make more sense for you in your mind and attribute and account for those 5 double bonds, then please do so. And you'll see that with carbon dioxide and water once we get to that. Anyways, 498 times 5 is 2,480. And what I'm going to do is, after I account for all the bonds and the energy required to break those bonds, I'm going to add up those numbers. And when I do that, I get 6,488 kilojoules per mole will be the unit there. That is the amount of energy that is absorbed in this particular reaction. Or in other words, it is the activation energy. And so I'm going to label that as the activation energy, or the amount of energy that is absorbed. Now that is just the first part or piece of solving this problem. So that is not the answer, but I'm going to use that to solve for my final answer. Okay, now that I've done the reactants, let's move on to the products. Okay, so on the product side, one type of bond that's seen is a C double bond to O. So I'm gonna write C double bond O, and the amount of energy for that bond is 805 kilojoules per mole. Oops. And I'm going to multiply it by how many of those bonds there are present in this reaction. So up here in this molecule, there's 1 here and then 2, except there are 3 carbon dioxide molecules in this particular reaction. So if you need to draw those out, just to make sure that you're answering this correctly, there are 1, 2, 3, 4, 5, 6 of those bonds present in this reaction. So 805 times 6 is going to give me 4,830 kilojoules per mole. Now I move on to my other product, and the other product is water, or H2O. And the type of bond that is present in that molecule is an O bonded to an H, or hydrogen bonded to oxygen. And the amount of energy involved in that bond is 464 kilojoules per mole. So I'm going to label that OH, and that's 464 times however many bonds are present. Now there are 2 bonds present here in that molecule, but notice here there are 4 water molecules in this particular reaction. And so I'm not going to multiply that by 2, I am going to actually multiply it by 8, because there are 2 of those bonds and there are 4 of those molecules. And once again, if you need to draw out each molecule and count it like this, 1, 2, 3, 4, 5, 6, 7, 8, you can definitely do so. I just want to make sure you're not getting confused by that. So 464 times 8, we get 3,712. Those are all the types of bonds, along with how many there are in the product side. So I'm going to add those up, and I'm going to get 8,542 kilojoules per mole. That is how much energy is released in this particular reaction, or in other words, the reverse activation energy. So I'm going to label this as reverse activation energy, or the amount of energy that is released. Now our ultimate goal is to find delta H, and so far we have done steps 1, 2, those were already done for us. We did step 3, and we did step 4 and 5 as well. That was finding the activation energy and the reverse activation energy, which we've done. Now the last step right here is just to subtract the 2, and this is important. You always do the amount of energy that is absorbed minus the amount of energy that was released. So right here, I'm going to write delta H equals the amount of energy that is absorbed, or the activation energy, minus the amount of energy that is released, or the reverse activation energy. So delta H here is going to equal 6,488 minus 8,542. Now I'm going to get delta H to equal negative 2,054 kilojoules per mole. And that is solving for delta H. A really important part of this is that negative sign. If it is negative, leave it negative. That tells you what type of process that this reaction is. And if you remember, if you have a negative energy output, then it is going to be an exothermic process. Versus if you come up with a positive number, you know that it's endothermic. Okay, so now that we have that, I'm going to draw the potential energy diagram for this particular reaction. Okay, so now I'm going to kind of connect this to our potential energy diagrams, and that's what we did last week, just so you can kind of see the relationship between what we just did and what you did last week. And on a potential energy diagram, you always start off with your reactants, and your reactants here are CH3, CH2, CH3, and O2. And those reactants are going to absorb a certain amount of energy, which is still labeled right here. We already calculated it. Release a certain amount of energy, and then it's going to form products. Now, because it's releasing more energy than it's absorbing, it's important to show that it is in fact exothermic. And the way I do that is by drawing my products lower than my reactants. And my products here are CO2 and H2O. And now I'm just simply going to label each of the different things that I've already calculated. Activation energy is how much energy is absorbed in a certain reaction, which we calculated to be 6,488. That is the activation energy. The reverse activation energy is how much energy is released when forming the bonds of your products, and we calculated that to be 8,542. And delta H is the overall energy exchange that is either absorbed or released in the reaction. And that is the distance from your products to your reactants, delta H. And in this particular example, it's negative 2,054 kilojoules per mole, showing you that it is indeed an exothermic process. So that's how this relates to the potential energy diagrams that we did last week. Okay, so that's example one. Let's go ahead and do one more, and then you can go ahead and try your Schoology assignment. Okay, so example two, we have a different reaction. We have HBr, and that is going to produce hydrogen and bromine in a decomposition reaction. And as you can see, the first two steps of this are already done for you. Again, the equation is balanced, and I've drawn those Lewis structures. So we're going to go ahead and start with the types of bonds on the reactant side. And on the reactant side, we look at the molecule there. There is an HBr bond, and the amount of energy needed to break that bond is 366 kilojoules per mole, multiplied by how many there are. And there is just one of those in this molecule. However, there are two of those molecules in this balanced chemical equation, meaning I'm not just going to multiply it by one, I'm going to multiply it by two. And remember, if you need to draw each of those individual molecules from the balanced chemical equation to make sure or clarify that you're getting the correct number of those bonds, please go ahead and do so. So 366 times 2, I'm going to get 732 kilojoules per mole. Now, since that is the only type of bond on the reactant side, that is the total amount of energy that is absorbed in this particular reaction. Or in other words, that is our activation energy. So I'm done with the reactant side. Now the product side, the first type of bond I see there is a hydrogen bonded to another hydrogen. The amount of energy in that bond is 436 kilojoules per mole, multiplied by how many there are. There's one of those bonds here, and there's only one from the balanced chemical equation. So I'm just simply going to get 436. I move on to the other molecule, and I see that there is a Br-Br bond. The amount of energy involved in that is 193, multiplied by how many there are. Once again, there's one there, only one in the balanced chemical equation. So I'm just going to multiply that by 1, get 193. Now I add those two together, and I am going to come up with 629 kilojoules per mole. And that is the total amount of energy released in this particular reaction, or in other words, the reverse activation energy. Okay, so now I've done all the steps except finding delta H, and delta H is equal to the amount of energy absorbed, or the activation energy, minus the amount of energy that is released, or the reversed activation energy. So delta H is going to be equal to 732 minus 629, and I am going to get a total of 103 kilojoules per mole as my delta H. And this time my delta H is indeed positive, not negative, telling you it's an endothermic process this time instead of an exothermic process. So I am going to make sure I show that or represent that on my potential energy diagram. You always start with your reactants. Your reactants are HBr this time, and that's your only reactant. And it's going to absorb a certain amount of energy, release a certain amount of energy, and then form your products. Now, the amount of energy that is absorbed is greater than the amount of energy that is released this time. So this time, my products are going to be higher up on this potential energy diagram than my reactants. It's opposite of that last example. And my products are H2 and Br2. Then I'm going to label my different numbers. This is the amount of energy that is absorbed, or your activation energy, which is 732 kilojoules per mole. This is the amount of energy that is released, or your reverse activation energy, which is 629 kilojoules per mole. And then the distance from your reactants to your products is your delta H, or the overall energy that is involved in this reaction, and it is a positive 103 kilojoules per mole. Once again, reaffirming that it is an endothermic process. Okay, so that is all the information you should need to do the Schoology assignment. This can be sometimes pretty tough for students, so if you have questions, please make sure you reach out via Schoology, email, or check into those Google Hangouts that I have. All right, guys, have a great rest of your day. I miss you a ton, and I'll talk to you soon.